Now, if somebody tells you that they have a turbine and say the turbine is 70% efficient, right? Should you believe it? Is that a good number? Is that a bad number? Now, versus somebody tells you, okay, my turbine is 30%, right? So I have an intuitive feeling of what is a ballpark number for this coefficient, right? Then we'll describe some empirical laws relating, say, the pitch angle to the coefficient, right? So the coefficient depends on the physical design as well as the pitch angle you're operating the blades at, right? So we'll describe and we'll take a look at that as well. Right, so recall from last time, basically we have a upwind and downwind. We want to find this coefficient, right? So how much power is capturing upwind and downwind? So obviously, right, you have more power upwind than downwind. So the power reduces as we go on, right? So then the question is how much does it, right? So we're going to assume that the mass flow rate, right? So from the mass flow rate of the air passing through the blade is fixed. Right? So you think of a moving mass of air flowing past through the wind turbine blades. We're going to assume that the same amount of stuff goes in and comes out of this area. Okay, so this is the same amount of stuff that goes in and comes out. Right, so air is not compressible. Air is, we're going to assume that this is not lost anywhere. Okay. So we have this being a constant, right? So basically the area that the air passes through multiplied by the speed of the air, then this is a constant. Right? This tells us sort of the rate of the mass moving through the system. Okay. So this being constant, basically we get, since this is a constant, so the speed and area are related by this equation. Right? So basically, if you look at the area upstream times the speed upstream, this is the area of the blade. This is the speed at the turbine or at the blades. Then this is equal to the area times speed downstream. Right? So all these are conserved quantities. Right? So these are some equations we'll use to get an understanding of how much wind we can extract in the blade. Okay, we'll understand that. Okay, so then since we have the equation, right? So since we know that the upstream wind is larger than the speed of the upstream wind is larger than the speed of the wind at the blades. This is larger than the downstream wind. Right? So we have this relationship. Then the envelope, right, the area contained there has to expand. Okay, so the speed keeps on decreasing. The amount of area has to increase. So we get this sort of air mass boundary out of it. Right? So it's moving slower and slower, but then we have a conservation, the same amount of stuff moving through the system. So the speed has to decrease, right? The speed decreases, so the area has to increase, right? So since all of these are constant downstream, then we have the area is smaller than the area. Right? So this area follow this relationship. Right. So so to be a little bit clear on what this means, right? So if you look at the air, the envelope air, eventually it comes down to the same size, right? So we'll expand once it goes past the blade, then we'll not expand forever, right? So this mass doesn't go forever. Eventually the envelope comes back to roughly the same size as before. But for us, we'll only consider to this point. Okay? So for us, we're only interested towards the sort of, until we're only interested until when you are still expanding. Okay, we're not going to worry about, how does it come back together, air mass envelope, how does it shrink, all that we're not going to worry too much about. Okay, so we're going to assume that there's volume air, it starts with a small area, and the speed decreases, so then the area increases larger and larger. Okay, so when we say downstream, it doesn't mean infinitely downstream. It means until we get, to the point where the envelope is the widest. Okay. Any questions about this? Okay, so this doesn't matter if you only have one wind turbine. This will matter, however, you have a far. When we have multiple turbines, then they have to be placed far enough such that the air mass envelope essentially comes back. Okay, right? So when we have one turbine, sort of once they pass a turbine, you don't really care about it. But we have multiple things. When you have multiple turbines in a farm, then they have to be placed not far apart, right? So this envelope comes back together. Okay, so for now, we'll only look at what happens when we have one turbine. But keep in mind, this is also a reason why the turbines cannot be too close together. Okay, they cannot be very close together. But basically, you need to wait until this mass of air, basically the area shrinks, down reasonably. The area shrinks reasonably down. All right, so this is our picture, geometric picture. So now we need to get some idea, right? So to understand efficiency, remember power we capture, we think of as the power upwind minus the power downwind in the air. So that sort of requires us to think about the speed of the wind at the blade, the speed wind at the blade. So this is an assumption we have to make. So what do you think a good assumption is? Right, so we have to make an assumption about the speed. We are not going to compute the speed in this class. So what is a good assumption to make to do some calculations, some ballpark calculations? Right, we know it's slower than the upwind speed. We know it's faster than the downwind speed. So what is a good assumption to make?
Like right in the middle.
Right in the middle, right? The average of the two speeds, right? So a good assumption to make, at least, from a first order calculation, right? First order calculation. We're going to assume that this is the average of the two speeds. Okay. All right. So this may not be, exactly correct, but it's not a bad assumption. It has to be in between the two speeds, right? So taking the average is not a bad assumption for the calculation we want to do. Okay. So we take this to be the average. Then let's see what happens. So we take this to be the average speed. All right. So this is average speed. Let's now look at it. So then we have the power, or the power we extract from the blade. This is the power upwind minus the power downwind. Okay, so this is the difference of the powers. Okay, so then the power upwind minus power downwind, how much power do we have? Well, upwind, we have half m over t, so half times the mass flow rate times the speed square of the speed. This is just the kinetic energy divided by t, which gives us power, minus 1/2 for the same amount of mass moving through times the wind downwind. Okay. All right. So then if you collect all this together, we get the power of the blade is half times this flow rate, right? Times this flow rate multiplied by the difference of the square. Okay, this is our flow rate. Now, how do we compute the flow rate? Well, so this F. Okay, so to compute the flow rate, we need the speed at the turbine itself. Okay. So the flow rate is m over t. This is the density of air times the area swept out by the blade, right? This area swept out by the blade is something we know, right? We know the size of the blade, we can compute this area. Okay, so this is multiplied by the speed of the blade, speed of the wind at the blades. So we're going to substitute the speed of wind with the assumption we made before. Okay, so this is our mass flow rate, right? This mass flow rate. So this puts in all the number, right? Then all the number is captured, or all the numbers depend on the upwind speed and the downwind speed. Right? So the F depends on W and WD. And the power of the blade also depends on WU and WD. So, right, so then we want to basically collect all this term together and see if something interesting happens. Okay, so let's see if something interesting happens. All right, so this is the typed out version of the equations. All right, so let's look at the power extracted. Okay, then how much power do we get? Well, we know the power of the blade as half times the flow rate times the difference in the square of the speed. So we're going to substitute the flow rate equation into here. Delta area of the blade squared. Okay, we're going to substitute this into there. Then we have the power the blade extracts as basically this big equation. Right, just power times this big equation. Okay. So it's a little bit inconvenient to carry two speed. Right, so now let's define gamma as a ratio of the downwind speed over the upwind speed. So this is some positive number between 0 and 1. If we make this definition, then the power of the blade, we work through this, right? So this is half delta AB times. So anytime we see the downwind speed, we're going to replace it by gamma times the upwind speed, gamma times W, W squared minus gamma, W squared. Okay, all right. So this is the equation we have. You may ask, okay, why is this meaningful, right? Well, what's important about this equation? Well, this equation is meaningful because now we can pull out a term. Okay, we're going to pull all the WU out, right? So we have one WU from the first bracket, a square from the second bracket. Then we multiply by this term, 1/2 1 plus gamma, 1 minus gamma squared. Okay, so now these are the two terms we have. The first depends on this W cubed. The second depends on this ratio gamma. Right, so this is the equation. We get this equation. So now let's look at this equation. What does the first term mean? What does this term mean? What is this term? Should look very familiar to you, right? Has a density term, has a cube of the speed, has an area. What does this term mean?
That's just the total power in the wind, right?
Yeah, this is the total power in the wind. This is the amount of power you can extract from wind if you pick up all the speed in the wind, right? This says if I put a blade, if my blade sweep out the area AB, and then I get all the power in this wind, right, at a speed of WU, then this is the amount of power I have. Okay, this is the amount of power I have. So this is just the power from wind. This is precisely the amount of power we can get from wind. Right? So if we lose nothing, if the system is perfect, 100% efficient, we get this number. Okay, all right. Then this naturally is the coefficient of performance. Right? This number now is something between 0 and 1. That tells us how well we do. Right? So this is the coefficient in the win, coefficient of performance. Right? So this is a coefficient that says, you don't pick up all the power in the wind, but depending on what this coefficient is, you pick up a fraction of the power in the wind. Right? You pick up this fraction. Okay, so this is the power extracted by the blade. Any question about this? Right, so this is an important relationship, and this is actually an important idea in power engineering calculations or in all engineering calculations. As often what we care about is the performance, as a sort of the fraction, the efficiency of the system, right? This is almost, matters more than the absolute amount of power can get out of the system. The way to do this is you basically want to write everything into this multiplication form. You want to write into the amount of total energy to power you have, multiply with some other number. Then you want to interpret the other number as a coefficient of performance. Right? This is what's going on here. Okay, so this is a good, if you go on work or you do research, this is a very common strategy of developing this kind of equations. Okay, so this is our common strategy. All right, so let's look at this coefficient performance. Right, this is 1/2, 1 plus gamma, 1 minus gamma squared. Okay, so this is our coefficient performance. So let's check this, right? So let's check it for some value of gamma to see if this makes sense. Right, we got this by doing a bunch of algebraic manipulations. Right, then after we do this algebraic manipulations, the first thing again we want to do is to plug in some numbers for gamma to see if this equation actually makes sense. Okay. First, make sure this is between 0 and 1, actually. I'm claiming this is a efficiency measure, so this better be between 0 and 1. Okay. Right, better be positive, better be between 0 and 1. Okay, so let's see if this is the case. Right, so if we do a sanity check, what are some of the good numbers to plug in to do a sanity check? I say I claim this as the equation I got. You want to do a sanity check on my equation? So, all right. So one is let's plug in 0. Okay, so that's a good suggestion. Let's say gamma equals to 0. If gamma equals to 0, what is this coefficient? This is 1/2. Okay. So it seems reasonable, right? It's some number between 0 and 1. It's 1/2 may or may not be correct, but this at least not obviously wrong, right? What other number can we check here? What other number can we plug in?
1.
1, right? Another good number plugging is 1. So gamma equals to 1 basically means the blade did not slow down the wind at all, right? So remember, recall gamma. Sorry, this as a downstream wind is a ratio of the speed of the downstream wind divided by the speed of upward wind, right? So being 1 means the blade did nothing, right? Did not slow the wind down. So this makes sense, right? If the CP between 0 means the coefficient performance, you're 0% efficient, you extract no power out of wind, which is the correct thing, which is what we expect to happen, right? Since wind did not lose speed, then conservation of energy tells us no energy is lost, right? So this is where, okay, so this makes sense. All right, so these sort of sanity check tells us basically that our derivation is probably correct. Right, so at both extremes, the number should make sense. And this is what you should do if you're doing some back of the envelope calculations. As you always after you get some equation, do a sanity check, plug in some numbers to see if it makes sense. Okay? So there's one more thing we can do. Right, we can ask, what gamma maximizes this coefficient? Right? What is the maximum amount of efficiency we can derive from this turbine? Okay, so let's max over this equation. Okay, let's max over this equation. So this is the, right, so then this is quite simple. We just need to take a derivative and set it to 0, and that will give us the equation, and this will give us a maximum. So let's do that. So then we have the product rule. This is 1/2, 1 minus gamma squared, minus gamma 1 plus gamma. Okay. So we get this equation. If we use the product rule to do this derivation, then we set it to 0. So this will turn out this. So this will turn out this, the maximizing gamma should be either 1/3 or 2/3. Turn out this gamma is 1/3. Okay, so turn out the maximum gamma you can, the best gamma you can have is 2/3. And then we'll turn out the maximum efficiency we can get out of the turbine. And no matter what the design is, no matter how efficient you make it, as you plug this gamma in, you get about 59.3%. If you just plug this in. So this is saying the maximum efficiency you can get from wind is about 60%. Right? You can do no better than 60%. Okay? So this derivation is actually quite a, this is actually a quite robust calculation because it made no assumption whatsoever about the design of the wind turbine. Made no assumption about the design of the blade. The only assumption we made is essentially that the speed at the blade is half of the average of the upwind and downwind speed. If you make this assumption, then everything else comes out as, from this assumption, you can do all the algebra. And this tells you that the maximum efficiency of wind turbine that you can ever hope for is 59.3%. Okay, so this is called the best limit. Okay, this is best limit. And this was basically it was how Best made the calculation. He was interested in how much power you can convert, and you get 59.3%. Right, so this tells you, if somebody tell you, hey, I have a turbine design that's 80% efficient, you probably should not believe that person. Okay, and right, so believe it or not, I have heard this. There are people who try to, sell me a product and they claim their design is like 85% efficient, something like that. So it's always good to have a theoretical upper bound on how efficient you can be. Right, gives us a number to shoot for. Right, so this is about 60% for wind turbines. Any question about this calculation?
Yeah, I'm still confused. How do you get a 1/2 for gamma?
How do I get 1/3? Or 1/2, sorry. Are you saying how do I derive this? So if you solve this equation, it turns out 1/3 is the solution of this equation. Right, so I want to take a derivative and set it to 0.
Okay, thank you.
Yeah, so it just turned out this solves it. So you can plug it in back and check. Right, you get the 4/9 minus 4/9. So this is just what it turns out.
Does the star mean the limit or the maximum value?
Star means the maximum value. So this is the maximizing gamma, right? So the limit is this 59.3%.
Yeah, okay. Thank you.
A star means the maximizer of the CP. Okay. Right, so this is again the fairly right. So this is why again, wind energy is a little bit easier to do this solar. To get a fundamental limit for solar cells takes quite a number of steps in quantum mechanics. Where for wind, it turns out to be fairly easy mechanical calculation. Right? The hardest part is maximizing a cubic equation. Right? So this is for a single turbine. For a wind farm, the calculations become much more complicated. Okay, so nowadays, if you look at a lot of the technology or a lot of advancement being made, it's not so much on a single turbine sort of scale. It's important, but a lot of work is going towards the farm scale. If I have 100 of these, I need to place them in a reasonable, over a reasonable amount of area. How do I do that? How do I do the control? Right? So that's, that's more difficult. That's a lot of where the work is going. Any other questions about this efficiency calculation? Right. So this is some good number to have in your mind, because in the homework or in the midterm, often you'll be asked to compute the coefficient of performance. So if you get a number that's larger than 59.3%, you made a mistake somewhere. Right? So there's some number to keep in mind again as a sanity check. So when you're asked to compute the coefficient of performance, it should be much lower than 60%. Okay. Right now, our turbines are not close to 60% these days. Right, so again, these are just the equations typed out in case my writing is not all that clear. Right, so we get the CP. Again, there's the coefficient. Of performance, right? So just the power the blade extracts over the maximum amount of wind power I have. Okay, so let's do an example. Right, so this example says I have a wind turbine, WT, I have a wind turbine. And somehow I compute the mass flow rate. Okay, so I know how much air is flowing through this turbine, flowing through this area. And I have a, upwind speed is 20 meters per second, downwind speed is 18.7. Right, we want to figure out how large the air mass envelope is. I want to figure out the wind power, the power captured by the blade. And we want to compute the coefficient of performance. So this is sort of quite standard problems you may see in this area. So let's do this computation. Okay. So let's figure out how large each of these envelope is, right? How much area do they occupy? Okay. So we know the flow rate as the area times the speed. And here in this question, we're given the speed, we're given the flow rate, and we want to find the area times delta. So I forgot about it. So this is density okay. So to find the area I have is this is flow rate over the speed times the density. We're going to assume density is 1 almost always. So okay, so this is a large area that we're looking at. Then we look at the right. So if you look at the downwind times delta. This is 18.7. This is about 70 meters squared. Okay, so not terribly different between the upstream and downstream. Okay, not terribly different because the speed difference is small. So the speed is quite close. The speed is quite similar. And then if we assume circular areas, then the radius of the circle upwind is about, or let's look at the diameter. It's about 35.7 meters, and the diameter downwind is about 37 meters. Okay, so if you assume it's circular, then you can compute the diameter of the circle, given the mass flow rate. So this is question 1. And question 2 is simply finding the power. Okay, so question 2 asks us to find the wind power, upwind and downwind. Right, so this is again, not very difficult to do. Once we know the area, right, we just plug in this equation, which is, speed relates to power in cubic fashion. So if you plug everything in, 4 megawatt for upwind, you plug this in, we get about 3.5 megawatt. Okay. Then it's easy to compute the amount of power we extract. Just this difference, 0.5 megawatts. Okay. So once we know the amount of power upwind, the amount of power downwind, subtract them, you get the power at the blade. Okay. So this is the case where you know the mass flow rate, right? So it's not very difficult to compute the, right? So not very difficult to compute the amount of power we can extract. Okay. So we know the amount of power we extract. So there's many ways we can compute the coefficient of performance. There's many ways to do that. So one way to do that is to plug into the equation we have. Right, one way to do that is to CP, say this is simply the amount power we have in the blade. Divide by the amount of power upwind, normalized by the difference of the ratio. Right? So we need to remember for the coefficient performance, we're not looking directly at the total amount of power upwind. We're looking at the amount of power we would have extracted of the area as the area swept out by the blade, and the speed as the upwind power as the upwind speed. Okay, so it's not just the power of blade divided by the power upwind. You have to do a correction for the area because we're considering a smaller area. Right, the blade we're considering a smaller area. Okay. So if you plug in these numbers, then we get 0.5 over 4 multiplied by 1,000. So let me compute the, right, so then we need to compute the area swept out by the blade. This is the flow rate divided by the power at the, divided by the speed at the blade. So the flow rate divided by the average, divided by the average speed, divided by the density. So we get about 0.6 meters squared. So the coefficient of performance, then this is 0.5 over 4 times 1,000. This is 6. So we get about 0.121. So 12%, about 12% efficiency. about 12% efficiency. Of course, another way to compute this is directly to use the gamma equation. Gamma squared. Gamma is the ratio of the speed, 0.935. So you plug everything in, we get the same number, 12% or 0.121. Okay, so this is different ways you can compute the coefficient performance. In this equation, since you can explicitly figure out the area, you can use the definition of coefficient performance, right? Just the power, the ratio in power corrected by the difference in area, or you can plug in this or gamma equation. You can plug in this gamma equation. Right? Any questions with this example? Okay, so this is a quite common example. You see, quite common example. The main thing to remember is often people forget about this area correction term. Okay, sometimes you tend to see a total power upwind and the power extracted by the blade. You just divide them and claim that's the right. Divide by them and say that's the efficiency you have. That's not exactly correct. You have to take into the area into account. Okay, the amount of power available in wind depends on the area. And the area we consider as the area swept out by the blade. Right? So there's always this area correction term. Or if you know the speed, if you can find out gamma, then you can use this equation. Okay, so different ways to do the problem, right? Okay, so this is one example. Then let's look at more closely to a wind turbine control. Right, so remember, if we're operating a wind turbine, we're gonna get some coefficient performance, less than 60%. But then exactly how much we get is sort of quite a complicated relationship. So the way we quantify that equation is through something called a tip speed ratio. Okay, so we're going to introduce another wording called the tip speed ratio. So what tip speed ratio does? It basically say how much power I can extract depends on the pitch of the blade, but for a given pitch, it also depends on how much my blade is spinning around. Okay, right, depend on this speed. So my blade is spinning at the faster speed, maybe I got more power. If spinning at a slower speed, maybe I got less power. Okay, so that's the tip speed ratio, right? This is called tip speed ratio. And this ratio, because we don't want to talk about the absolute speed of a blade, we always want to reference to the upwind speed. Okay, so this is basically the speed of wind coming at me. Then I have this blade spinning around. So I want to figure out what this ratio is. That characterizes how fast my blade is going. Okay, so the key thing is this: how fast or how slow is a relative quantity. It's relative to how fast the wind is blowing. Okay, so we're going to divide this by the speed of wind. All right. So this is called the tip speed ratio. So this has a lambda, is called the tip speed ratio. And turns out lambda, we talk about lambda, it's because the speed of the tip of the blade is relatively simple to compute. Right? It's relatively simple to compute because we know the rotation frequency. Okay, we know the rotation frequency, right? We know this n, this is in rotations per second. We know how fast this thing is turning. We know how long the blade is. So as the tip basically moves in a circular motion, you multiply 2 pi by the turn speed. You get speed in radians per second. You multiply by how long the blade is, right? You get the tip. Okay, so we got this equation. Then tip speed ratio is simply this. The tip speed ratio is the ratio between how fast your tip is moving relative to the income wind speed. Right, so that's just sort of a natural way to talk about how fast my blade is turning. Okay, we often, we talk about blade turning being, let's say, 30 RPM, but that's an absolute quantity, right? So a relative quantity, relative to how much wind we have, is through this ratio. Okay, so you see this quite often. If you go out and buy a wind turbine, you'll see a data sheet that characterizes, that basically has a bunch of curves that depend on this lambda, the tip speed ratio. Okay, so the way this is used is basically the following. So I can compute this tip speed ratio. Let's compute this tip speed ratio, right? Then let's look at the coefficient of performance. Yeah, let's look at coefficient of performance. This is, recall this is in the gamma formulation. Okay, that's in the gamma formulation. Then what we want to do is we have that, so we want to relay basically gamma to lambda. Okay, we want to relay gamma to lambda. Right, so another way to write gamma is, okay, so recall W as 1/2 of the average of the speed. So I can replace WD as 2W minus WU. Okay, so that's possible. I could just another way to write WD. So substitute that in, I get this is 2 times W over WU minus 1. Okay, 2 times W over minus 1. So lambda is the tip speed divided by the incoming wind speed, the upstream wind speed, upwind speed. So this, you can do another substitution. Basically, you substitute W into this thing. What we get is gamma is now 2 lambda V tip minus 1. Okay, this is just a straightforward substitution. Right, you see WU, you substitute W equals V tip over lambda. Okay, you get a function for gamma. You put all this in, this is, so you substitute gamma from lambda into this equation. V tip 1 minus 2 lambda V tip minus 1 squared. Okay, you get this number. All right, so this is the number we get. Okay, so this tells us what the coefficient of performance is. Well, we can compute this coefficient of performance. So why did I do that? What is the point of this substitution? Right, this seems just to be a bunch of equations, right? They all equal each other, that's true. But why is the equation, let's say in terms of lambda, the tip speed ratio, why is that better than say the equation in, the original equation in CP? Why is one better than the other? Can you see some benefit of using the equation just depending on lambda and the tip speed ratio?
You don't need like the wind speed up and downwind of the blades. You just need the one wind speed.
Right, so you still need the wind up of the blade, right? You have the lambda there, but you don't need downwind speed. You don't need downwind speed. So upwind is easier to measure. Put a sensor in front of the turbine, you can measure it. You need the wind speed at your turbine, which presumably you can measure. Right, from that you can compute CP. Okay, so that saves you another measurement downwind. You don't need to go and measure downwind somehow. Right, so this as a better formulation in the sense that V-tip is something you can compute by measuring the blade, right? The wind speed is something you can compute by measuring the blade. So you save yourself from this ratio, right? You don't need to measure, you don't need to measure the downwind speed. So this is sometimes a little bit easier to work with compared to the other coefficient performance. All right, so, but both of these are, equivalent. These are equivalent things. So we have, if you plot this thing, you get this sort of curve with one thing in the middle, right? And then our goal is to operate close to this region. Right? So we want, if you look at the tip speed ratio, that is not the faster is better, it's not the slower is better. As there is a sort of sweet spot in the middle, you try to track. Okay, so this is you can think of this as maximum power tracking if you want, right? So I know my coefficient performance, I want to extract maximum power, peaks in the middle of the speed. So then our goal our goal of looking at of controlling the turbine is to make sure the turn rate of the turbine hits this sweet spot. Okay, we want the turbine to turn at the right speed so I can extract most power out of it. Right? So this is the idea we want. How you do that is you control the pitch. So basically you turn the pitch a little bit. That controls how fast you're spinning, how fast you're going. And the speed of rotation tells you where you are on this curve. And you want to be in the sweet spot of the curve, right? You want to be in the sweet spot of the curve. Okay, so this is how we do power control. Right? This is how we do maximum power control. Right? So this, so you look at the sort of the gears and the software for the turbine. Some of it doing this maximum power tracking. Right? So you're not going to always hit the maximum exactly, but you don't want to operate too far away. Okay, you don't want to lose efficiency. Okay, so this is another thing for engineering. Right, we want to figure out what is the most efficient way to do things, and then have some measurable feedback control we can have to keep track of the maximum efficiency. Any questions about this? Okay, so if not, let's now break until 1:30, then we'll resume the rest of the class. Okay, so I'll be offline and I'll be back in 2 minutes. If you have a question about homework, I'll be back in 2 minutes. All right, so let's get started again. Okay, so remember we can power or the coefficient performance depends on tip speed ratio. And if you look at the region of operation of a wind turbine, basically we'll see as there are several distinct regions. Right? It turns out as if the wind speed is too low, you generate no power. Okay, you're off. Right? So this is region 1 is your turbine is off. You cannot generate, a tiny amount of power. So you have to generate some finite amount of power. So that's region 1. Region 2 is you ramp up steadily. Region 3 is you hit the power capacity. There's a maximum amount of power you can generate. And normally you like to operate in region 3. Well, you don't have to operate in region 3, but to get the maximum power out, you operate region 3. Region 4 is the wind speed is too high, and you have to shut down a turbine. Right? So again, the idea is it's not the bigger the wind speed is better. Right? For everything, there is a correct range of operations. And for wind turbines, there also for any turbine there's a range it likes to operate in. All right, so if you recall, because we want to track this maximum coefficient performance, right? We want to track this. So nowadays, if you look at turbines, they are all variable speed turbines. This means if you look at the rotation rate of the blade, they can be variable speed. They don't have to rotate at the same speed, right? If they can rotate at different speed, they can basically change their tip speed ratio. That means they can track the maximum CP, maximum coefficient performance. So there's two ways to do it. One is you have electronics. Basically, you have electronics inside the turbine that does a bunch of conversions. We'll cover this later. We'll go into how electronics work. Another is changing the pitch angle. Okay, so the pitch angle is actually sort of the quick and dirty way to do this. So it's not, it's a mechanical gearing system, but mechanically, you have a blade, you turn it, change the pitch angle. This will change how fast it spins, right? And that shows up as a change in the tip speed ratio, which changes where the maximum CP occurs. Okay, it changes where the maximum CP occurs. Right? So if you look at the diagram, is if you keep changing, so beta, these different betas are the different pitch angles, right? Then thing to remember is the tip speed ratio is a function of beta, right? By changing the pitch, I can get the blade to spin faster or slower. Okay. Then because this is a function of beta, if you look at the curve is sort of, changes where, changes how they behave. Right, so there's here the red curve is small. Sorry, the red curve is a larger beta. The blue curve is smaller beta. So by changing beta, you have different places. You can place the curve at different spots. So changing beta give you, a difference in CP. Right. So obviously we don't know the closed form formula. We don't know how what the closed form formula is for CP. Okay, we don't know that. This is an empirical formula. You don't have to remember anything about this formula, except it's here. And you may need to look up these numbers. Okay, so the homework, if I make a homework, I may get lazy and say use the empirical formula for CP in class. That means this formula. We're just plugging all these numbers. Okay. Why they are what they are, I have no idea. I have no idea why this is the form people chose. I've been told as, if you look at the reference book, Muhammad al-Shakawi, Professor al-Shakawi, apparently the story is he was one of the earlier folks designing wind turbines, and he went and fitted this curve. Okay, so somehow he got this curve, and we're going to use this curve. Right? So nowadays, of course, you don't do it this way. Nowadays, you probably train your network on this and get a CP, get a relationship between tip speed ratio and the CP. But none of it is that's right. So that doing that way and fitting this empirical formula, they're equally good. So this is just for you to know if the homework or the exam, since it's open book, says use a formula for CP, use a formula to find CP, refers to this formula. It refers to the specific formula with all the specific coefficients. Right. This is just the way what the beta turns out to be. Right, which people just chose this formula. Okay, so not much to say about it, except that we do have one formula. Okay, so there exists a formula for us to use. Okay. Right, so this depends both on the tip speed ratio and beta. Okay, so of course the tip speed ratio and beta depends on each other. So this is trying to cap. That's why this equation looks so complicated. Okay, so just some empirical formula to know, and you should know where to find it. Right, so maximum power tracking basically is, as we said, you want to operate at the highest point of the curve. So you keep changing your lambda to track this highest point. Right, so that's the maximum power tracking. Okay. Then if you look at the impact of the number of plates, okay, look at the impact of number of plates. It does matter a little bit between 3-blade turbine and 2-blade turbine. Okay, so remember, we are looking at efficiency, right? So, again, the maximum you can get is 1 in this case, right? So we're looking at the coefficient performance versus the maximum possible you can extract. It just turns out the 2-blade turbine needs to rotate at a higher speed. which makes sense because you only have 2 blades. So you need to rotate faster, basically, to sweep through the area. Okay, so we just, that's why we have, that's why, two blade turbines need to rotate a bit faster. You achieve this at a higher tip speed ratio. Right, so but in practice, most likely we'll see 3 turbines. We'll see 3 blade turbines. So why is that? Why is that we don't see, 2 bladed turbines? Keep in mind that a blade is really expensive and hard to install. Right, so why don't we see many 2 blade turbines?
Doesn't have to do like stresses, some kind of physical stresses that I don't understand.
Right, okay, so if you look at, right, so that's the right answer, right? It has to do with stresses. So what does that mean, right? So let's say this is my 2 blade turbine. So this is my pen, this is my pencil, right? So if you 2 blades, it can be horizontal or vertical, right? It can be this kind of thing. However, the mechanical stress on a horizontal position and the vertical position are different, are totally different places, right? So here, right, the mechanical stress is, going downwards, hanging like this, whereas here, so everything lines up. So what happens if this thing rotates? Sort of wobbles back and forth like this, because the stress is different. Okay, because the stress is not uniform depending on which position your blade lies in. It sort of wobbles back and forth as it turns. Okay, so you have this wobbling motion, right? If you have something that's say 50 or 100 meters long, you really don't want this kind of wobbling to happen. Okay, mechanically, it's very bad for the system. Okay, so that's why we only see 2 bladed turbines for relatively small wind turbines. If your turbine is small, you do see a lot of 2 bladed designs. It's easier. You don't need to mount 3 blades onto it. But for larger things, because if we have sort of 3 blades, you always know the stress is much more uniform. Okay, there's sort of no 2 distinct positions you can be. It's more uniform. Whereas in 2 blades, it just wobbles around. And so I guess you really don't want to see that once it gets too big. And so that's why we don't see many big 2 bladed turbines. Smaller ones we do see, we don't see many big ones. And there are sort of other, fancy designs that may have a sort of more continuous structure, but it's for us, we'll stick with 3 blade turbines. Right, so there's something. This is again a sanity check. Yeah, go ahead. Yeah, anybody has a question?
I just have a quick question. So the performance coefficient in this case, is it 100%?
No. This is to the maximum.
Okay, so
that's some maximum you can get.
Okay, and so I guess what does the 1 represent here? Is that just the maximum of the 59.3% efficiency?
No, so this maximum, just from, let's say, some number like this, right? It's wherever the top of the curve is.
Oh, okay, so
right,
it's not the absolute max.
Yeah, not absolute. So this is a ratio. So this is one number.
Oh, okay,
Yeah.
Makes sense. I didn't see the. Okay.
Yeah, so there's a line between this. So this is a ratio between these 2. Yeah, so that's again a check to know that you have less blades, you need to rotate faster. Right? So that's just this check. So again, we don't have 4 because of turbulence problems. So that's why everything is 3 bladed. So maximum power tracking, again, as if you look at the curve, basically is trying to maintain us at a high power region or try to get as much power out of as possible. Okay, so we're always doing maximum power tracking, both in wind and solar. In solar, you also do maximum power tracking, although the mechanism is quite different. Right? Although it's quite different mechanism. So if you look at the control diagram, basically the control diagram is you control the pitch you have. Right? We have some pitch we want to control. Then the control laws look at how much what you're spinning at, what your rate should be, how much power you're generating, what the sort of the set power point is. Altogether, they tell you should you increase or decrease your pitch angle? Okay, so this is the control logic we have inside the turbine. Right, so if this is actually very important logic. If this logic breaks, then the turbine fails to work. Okay, so this is quite important. This control logic is quite important to make sure this is set correctly given a turbine. Right. So this is the logic. We won't go too much into detail about what exactly controller is. We'll talk a little bit about this once we get more into power electronics. But now just remember there is some control logic to do this. Okay, there's some logic to do this. And any questions about the controller design? Okay, so 2C examples of when things can go wrong or what happens when things go wrong. Again, Google wind turbine failures, quite spectacular. So go to YouTube and watch those. Quite spectacular. You literally see the blades getting torn off the tower. You literally see the blades getting torn off the tower. And this is another issue when people fear about cybersecurity, right? So, if you want to cause a security issue, right? If you are, when you want to hack the system and you want to break the wind turbine, the way you would do it is to hack this control logic. Basically, anywhere you see a minus sign, make it into a plus sign. And this can be done in software. This is entirely software. If you do this, you'll see the turbines being, torn off the tower. Okay, you see turbines flying off the tower, right? So when you have this kind of control logic, that's also when at some point people raise cybersecurity concerns. Right? So it's not right. So it's not that hard to destroy a multi-million-dollar equipment. And for this wind turbines, they'll probably wipe out a lot of things around it. A big wind turbine. So this is where you need to engineer the logic well, and then you need to think about some of the cybersecurity issues around it. Okay, so there's just a note for us. We're not going to go into all this, the cyber issues, but something to keep in mind. Okay, the turbine works because of this sort of negative feedback logic, right? And in practice, if that thing breaks, the whole basically the blade just flies off. You see the blades flying off the tower. Okay. Right, so this is the pitch controller mechanism. Then we implement some integral control. There's an integral controller sitting there, right? Okay, so that's all about a single turbine, right? So as a reminder, how a single turbine works is there is some maximum amount of power we can extract from wind. We cannot get 100% out of it, right? Far from it. The limit is about 59%. Then, how much of this 59% we actually get depends on the pitch angle, because it depends on the tip speed ratio. Okay, so then we control the pitch to control the tip speed ratio, try to track the maximum coefficient of performance. Okay, so that's sort of how a single turbine works. That's sort of the working principle of a single turbine. So that's right. So now let's look at what happens when you have more than one turbine. Okay, so you have many turbines, what happens? So most of this comes down to how far apart they have to be. Right. So this is, so how far apart they have to be. And the reason we have farms, they just reduce the overhead cost. Right. Instead of, you install one turbine, pull a transmission line to it, install another turbine somewhere completely different, pull another transmission line to it. You just concentrate them all together, so it's economically much cheaper. A lot cheaper maintenance cost, right? You can do all the maintenance together. The grid connection is quite simple, right? So now we basically want to have large farms. Makes economically much more viable to have large farms. Right, so so you see this both offshore and onshore, especially the offshore ones are getting quite large. Sometimes you have many turbines all together, connect to each other. Right, and the engineering challenge is that you have a lot of turbines, then they disrupt each other, right? They are basically changing the wind flow once they pass through them. And this has consequences to the turbines downwind from it. So it just, wind slows down. You may have turbulence. You may have sort of very weird mixing of air if you have, the air is not blowing directly at a turbine, right? So the airflow can get complicated, right? And the way we deal with it is just to place them far apart. Okay, one way to deal with it is just place them sufficiently far apart such that they don't impact each other. They don't impact each other, right? So if you look at the placement, it's easiest to think of things being placed on a grid, on a square grid. Okay, it doesn't have to be, right? So if you look at the pictures, obviously this onshore one is not in a square grid. But for us, for simplicity, we'll think about placing things in a grid. Okay, we'll have a square array. The distance between the turbines this is d, right? And our separation is again a relative quantity, a unitless quantity, right? So this separation is basically the distance between turbines over the diameter, right? Over for how big the area blade sweep out is. Okay, so that's a unitless quantity, and we want a rule of thumb guiding how large this has to be for them not to impact each other. Okay, so the way you would do this, again, a lot of times is done by empirical analysis. It's challenging to analytically, work out the relationship between separation. So this is S equals D over 2R and the efficiency. So we know the larger the separation, the more efficient it is. How this curve exactly goes, often we get a table like this and read it off it. Okay, so people will have testing locations, right? We can test them. We can do fairly realistic simulations, actually. We can do simulations. And then after doing this simulations, we can figure out how to get a table like this. Okay, so we're gonna read off the table this way. Okay. So of course, the higher the larger the separation, the more efficient you get. But of course, the larger the separation, the less number of turbines you can install. Right? So the trade-off is you want them to be efficient, but you're also reducing the number of turbines you can put in. So there again a sweet spot. Okay, there is a sweet spot. Right? So we can compute sort of the total area, the land we need, if given a certain distance between the turbines. Right? We can compute sort of how large it is. Right? So this is the amount of land we need, and we want to figure out, based on the amount of land we have and the efficiency, we want to figure out some sort of rule of thumb of how large the separation is. Okay. So if you look at industrial practice, we're going to assume that wind comes in one direction, okay, coming in some sort of a set direction. This is not a bad assumption because a lot of places we choose to install wind turbines, the wind direction is fairly well defined. Okay, so we're not going to install turbines at places where the wind just blows randomly, right? We're going to choose to install them where we have sort of good, consistent wind. So in the prevailing wind direction, in the direction where wind normally blows at, the separation, right? So in the direction perpendicular to it, you can get away from, using a small separation, maybe 6 times the radius or 10 times the radius. Whereas in the direction of wind, you need to be longer, 10 to 20 radius, to allow the wind to pick up some speed. Okay. So if you look at the array, basically it's not exactly square, right? The separation is not equal. It depends on which direction wind is blowing. In the direction wind blows, you need roughly, fairly far away. In the direction that's perpendicular to wind, it's about 6 to 10 radiuses. Any questions about this? Okay, so let's do one sort of simple example on this. Right? So let's say, we have a 10 by 10 wind farm. So here we're going to arrange in a square array. Okay, we're going to arrange in a square array. Has a separation factor of 7. So this means d over 2r. This is 7. The distance between them is 14 times the radius. We're going to say that the turbine efficiency is, so this turbine efficiency. So this 85% is a mechanical to electrical. Okay, so the CP, this is the CP associated with wind. And the turbine efficiency 85% is the conversion from mechanical power to electrical power. Okay, so that's the 85% we have. And the wind power density is 1 kilowatt per meter squared. Okay, and the amount we want to compute is the power production per unit area of land. Okay, so this is saying if you're going to buy land, right, you want to figure out, given this piece of land per unit area, how much power am I getting? Okay, so this is the power density with respect to the real estate you have while building turbines. Okay, so let's see what this is. So first of all, let's see how large the land is. Right, let's see how large the land area is. So D is 2R times S. So this is 14R. Right, this has the, right, so this is the amount, this is the separation. So the total area of land required by this 10 by 10 array, this is 9D plus 2R, 9D plus 2R. So this is the square, this is the area of land I have. This is 1434 R squared. So we're going to carry the R squared. We're going to carry the R squared. It turns out it's not required for this question. We're going to carry the R squared. Then I have total 10 by 10, 100 turbines. I have this many turbines. So let's look at how much power I generate. Okay, so the power for the farm is 100. Not 1,000. This is the number of turbines I have times 0.85. Okay, times 0.85. This is the electrical efficiency times 0.4. This is my CP, coefficient of performance, and how much power I extract, coefficient of performance. And then if we want, let's look at array efficiency. So because they're in array, let's look at what the efficiency is. So go to our table. Let's say I trace amount 10 by 10. I get this point. I get this point. So let's say this is 80% efficient because I have an array, right? I can go to this table and look it up. So array efficiency, this is 0.8 multiplied by the power I have, right? I have 1 kilowatt per meter squared. multiplied by pi r squared. Right? This is the total amount of the power in the farm I have. So this is, if you do everything together, this is 85.45 r squared kilowatts. Okay, so then I have the power production per area. As the power I can generate over the total amount of land area I need, divided out 5.2 watt per meter squared. So this is the calculation for this question. Okay, so 5.2 per meter squared is not that great, right? Of a given the amount of land you have, right? So, so this is trying to say that even though each turbine seemingly generate a lot of power, because if you have many of them, they need to be far apart, then the density, power density per land area is often not that high, maybe lower than what you have expected. Okay. Any questions on this?
Quick question about the calculation.
Yeah,
Wouldn't it be 5.2 kilowatts?
Did I divide correctly? 5 watts, right? So this is 58.45. Right, so I have kilowatt up top, but I have 16,000 down in the bottom.
Oh, okay, thank you.
Yeah, so kilowatt, you multiply the top by 1,000, you get about 5.2 divided by the bottom. Okay, so you will see this. You will definitely see this in the homework and the midterm. This is a common, again, back of the envelope question that people do when they're looking at a piece of land and seeing whether it makes sense to install to build a wind farm there. Right, it's quite common to look at this type of question. Okay. So here, basically, the array efficiency, we eyeballed it off this graph. So if you see this in the homework or you see this in the exam, I will tell you what the array efficiency is. Okay, so you'll be told what the array efficiency is. You don't have to eyeball it off that graph. Right, so here is, since we're all doing together, we're just going to eyeball it. Right? If you actually get this question, you'll be told what that efficiency is. Okay, any other questions? All right, so today we'll get started on the next topic. Maybe not into a lot of depths, but let's get started in the next topic. A sort of change of, it's a shift. So next topic we'll look at statistics, okay, probability, basically, probability. And this you should read as wind or solar. Okay, so none of what we say is particular to wind or particular to solar, right? It's a way of thinking about the randomness. Okay? Right, so last part of the class we said, okay, given the wind speed, we can relate to the power we can generate, right? But the thing about wind, the speed is never constant. Okay? Even if you're offshore, you will have variations in the speed. Okay? So we need a way to talk about this kind of quantity, speed or power, when it's not a constant value. Right? We need a sort of formal framework to talk about this, right? To talk about speed or power. So that's why we're going to look at a little bit into probability. Okay, so if you haven't taken probability, it's okay. We're going to do things from first principles and without going into a lot of details. Right, so our probability is something like this. Basically, I can go measure the wind speed, right? So I can go and measure the wind speed. I can measure the frequency count throughout the year. So this is a histogram. This says I went and measure the frequency for a year, the wind power for a year, and there's a number of counts I have. So this forms basically so-called distribution of the wind speed, right? There's some distribution. So we're gonna do a bunch of calculations. We're gonna do a bunch of calculations with this as a, given this, given that we have this sort of distribution information. Now, what does it? How do we think about things like average speed? How do we think about things like variance? How do I think about things like correlation? This kind of questions. Right? Just a simple, simple ways to get us thinking about, to reason things probabilistically. So, right, so even though things are simple, it's good to have an understanding how to think about randomness, right? How to think about probability of occurrence, right? So if you're an engineer and you operate wind farm, and you tell your manager that, oh, there's a 10% chance I have no wind tomorrow, you should be able to explain what that means. You should have understanding to yourself what that means. Okay? So that's a probabilistic reasoning. Okay? So the first thing we're going to look at is something called discrete distributions. Okay? Discrete distributions. Discrete distributions are basically extension of the simple coin flip models, right? So the coin flip, you flip a coin, right? Have a fair coin, half the chance is head, half the chance is tails. So there's two outcomes, two possible events, and then we'll assign probability to them. So we're going to think of wind and solar essentially in a similar way. There's a bunch of different outcomes. If I go and measure the wind speed for tomorrow, there's a bunch of possible outcomes, right? And given this, we want to assign probability to this outcomes. I want to assign this probability to the outcomes. And then we want to do calculations based on this probabilities. That's all we want to do for this kind of problems. So the last thing we'll do in this class is think about, basically try to distinguish between coin flips and wind power. So when you flip a coin, you get head and tails. Okay? There is no numerical relationship between head and tails. Right? So when you flip a coin, you got two distinct events. There need not to be a number associated with the outcome. Okay, we can say head or tail. Right? There need not to be a number associated. Actually, often, when you think about probability, there may not be a number associated. Right? So, flipping coin, or let's say you're looking at the general election modeling, what's the percentage of somebody winning? There's only two outcomes, but there need not to be a number assigned with it. Right? We assign a probability, 50% is heads, 50% is tails. But the heads and tails themselves do not have a numerical significance. They're not numbers. They're just different category of things. Whereas for wind, we assign a number to the outcome, and the number makes sense. Right? So for wind speed, could be 1 meters per second, 2 meters per second, 10 meters per second. Well, these are numbers. We'll add and subtract these numbers. And so you don't add and subtract head and tails, right? We don't say head plus a tail. But for wind speed and solar power generation, we'll add and subtract numbers associated with the outcome. Okay, so the outcome is always a number we look at. Right? So that's called a random variable. Basically, something that has both probability of happening, and the outcome as a number we can do algebra. Okay, so that's what distinguishes wind versus drawing balls out of a urn or flipping coin or things like that. Okay, just a number. We'll have a number associated with. Right. So that's the idea we'll have. Then so we'll go into more depth next class, looking at some simple probability concepts. Things like mean and variance and sort of the Gaussian distribution, and some other distributions that you may not have seen before. Okay, so we'll do that all next class. As a reminder, the first homework is due tomorrow night, tomorrow 11:59 p.m. Okay, all right, thanks guys.